Shamash again, because you can't have too many Shamashes. And Hero, other people in the audience, welcome. We'll get cracking in just a minute. Please do ping your friends in, trade in your horrible orange ticket if you haven't already for the Scientific Discourse House, which is a house here on Clubhouse where we will talk about science in a civilized way. The clue's kind of in the name. Today I'm running the session because John is otherwise indisposed. Is that right, John? You are unable to run but able to join in and make sure that I don't ruin your series.
That's exactly right. I'm riding herd on you, though, Ben. So just know that.
Yeah, yeah. So my job is to make sure I don't undo all the good that John has done over the last long time, yes, try and inject you with more good physics. So today I thought brain teasers would be in order. I've got 5 of them for you today. The room will last about an hour and a half, something like that at the most. So we have about 15 minutes per brain teaser, something like that, and we'll see how it goes. Lots of interaction would be great. Lots of using the chat to submit your answers, and yeah, we'll get on with it. Anybody else on stage want to announce anything, say anything, ask anything, observe anything, whatever, before we get
Just
cracking?
that we're live on YouTube as well. So yeah.
Oh, fantastic. Okay, thank you very much for doing that, Shamash. I appreciate it. I'm sure John does too. All right, cool. So let's, what should we do? Why don't we just chat for a couple of minutes while we wait for people to come in? People are typically late. Why don't anybody else on stage just like introduce themselves or say whatever they want to say about any upcoming rooms? Yeah, and then we'll go from there.
Well, maybe I was mentioning I am my wife and I are getting packed up from our little B&B in Vancouver, and we'll be making our way over to the cruise terminal pretty soon. So we're gonna get on a boat and have a couple weeks cruising up to Alaska, see what seaboard looks like. Andy was telling me that I'm gonna have a good time there, so I'm hoping that turns out to be right. Oh, and I just maybe just a quick side message to Andy. Andy inundated me with a bunch of fish YouTubes, which I've finally gotten around to watching, and I think I am becoming a fish fan. So thanks, Andy, for that.
Is this literal fish, as in swimmy things?
PHISH. It's a band that does kind of progressive rock, Grateful Dead
Ah,
inspired progressive rock, maybe. I don't know. It's hard to describe, but pretty
It's
impressive
almost like a next
musicianship.
generation Grateful Dead kind of thing.
Yeah, really amazing stuff. That Divided Highway. If you listen to nothing else, to me that was spectacular. The musicianship in there is extraordinary.
That's one of my favorites and one of their standard uh, composed type songs. If you watch multiple versions of that song, they're not that different from each other typically, which is a little rare for them.
Right. I was thinking exactly that. I mean, I was listening for anything that sounded like a jam, and there was nothing in there except for maybe one that could have been extended, one stanza or something. It was
There's a
choreographed
yeah.
and completely, like rhythmic, and yet everybody was on the whole time. Really impressive.
Is
Very
the song The Divided
few.
Sky, not The
Yes,
Divided Highway?
Divided Sky.
Divided
Yes.
Divided Highway, is that it? Maybe
No,
no, I think it's
no,
Divided
no.
Sky.
Yes, you're right.
Yeah.
I didn't know about it, but I was looking it up, and something you wouldn't find out of another community. But I looked it up.
Yeah.
okay,
You
cool
did your
guys.
own
So we've
research,
got a
right?
reasonable chunk of people in the room. Why don't we crack on and start talking physics, just in case anybody's coming in and wondering why on earth we're talking rock bands. But do share the name of that band in the chat at somebody, so that other people can check it out, or a link to a video, including me. I'd like to check it out. So that'd be wicked. Oh my god, I've got a lot of tabs open here on Club Deck. Let me close 20 of them. There we go. Fish like that. Great, thanks, John. All right, dude, let's do it. So there's a link at the top of the room and a link in the chat a little while ago, about 8 minutes ago, to the slides. So if you want us to get to the slides, you can. Not 100% necessary here. They just help with the wording of the questions and so forth. The first one then is about a water bridge. So this is a canal that's a bridge that carries water, basically, so that ships can go over another span of water, or perhaps they can go over a road or a railway track or a ravine or whatever, a canyon, a bridge that carries water. So the question is, they designed this bridge and it may be designed to carry, let's say in our case, 10,000 tons of water. Question is, how heavy a ship can that bridge take? Assuming a ship, there's no gates either end, there's no sluice gates or anything like that. The ship just trundles along. You've got a 1,000-ton ship or a 2,000-ton ship. What's the heaviest ship that this water bridge can take, and why? So answers in the chat, answers in discussion, in voice, whatever. Let's discuss the heaviest ship. Assuming the ship can float on and off the bridge, what's the limit to the weight of the ship that this bridge can take? So I'm starting us with a little bit of a trick question, which is a hint, but it's interesting to think about. So Hero's saying any weight. Anybody else want to fire in some, makes an answer, also be prepared to back it up. So that's great, Hero. We can hear your why in a minute. Anyone else want to suggest a weight? So depends on the height of the water line, not the ship. Okay. So the actual wording of the question goes, sometimes a canal is guided over a bridge called a water bridge, but how heavy a ship can it take and why? Assume the level of the water on the bridge remains nearly constant as the ship crosses it. Assume the level of the water on the bridge remains nearly constant as the ship crosses it. Let's say there's 10,000 tons of water on the bridge before the ship passes. A 1,000-ton ship crosses the bridge. What is the extra load on the bridge when the ship is in the middle, and why? So
Maybe just a note of the kind of meaning that you have to learn to take as a student of physics to the level of the water remaining nearly constant. There's a hint in there that you may or may not take, right? But when you say nearly constant, what you really mean is assume it is constant.
yeah, I'm going to even take out the word nearly just to save
Yeah,
any arguments.
but it's funny because we do say nearly, right? That in the wording of a problem like this, it's very typical to say nearly constant or a thin wire or anything like that means a thin
Ignore
wire
it.
means a wire with no thickness. Nearly constant means no change.
Yeah, and that makes me want to add something to my third puzzle, but I'll do that later. Okay, so Hero, you answered. We've given other people a chance to answer. Do you want to tell us why you think why you think any weight of ship could pass?
Well, if the ship wasn't there, more water would be there, and it will weigh the same as the ship.
Yeah, are there any assumptions in that? Do you think? I mean, I can imagine a ship that couldn't pass. I can imagine designing a ship that would break the bridge. So what
Well, I mean,
assumption? So if
assuming
I
the
have a
ship
bridge,
would be able
I've
to
got a
fit.
ship. So I've got a ship. It's what happens is this ship it's got wheels as well, and the bottom of the canal is concrete. So the ship, most of the ship's weight's on the wheels, and a little bit of the ship is kind of floating in the water, and it weighs 1,000,000 tons. Can that ship pass?
You said ship, not bus.
I did say ship, not bus. So one assumption is the ship's not touching the bottom, which is, I think, a fair assumption. It's not scraping along yet. So on that assumption, and on what other assumption? There's at least one or two other assumptions in here.
There's the assumption that it's always floating.
Yep, I'll give you that. Similar to it's not touching the sides, it's going to probably be doing one or the other. Yep. There's also a little bit of an assumption about the water. As the ship comes onto the bridge, the water's free to do what it likes. It's free to move off the bridge, right? So the ship, as the ship comes onto the bridge, the water that it's displacing goes somewhere else in the canal. Anything else comes to mind from anybody? Do we buy this? I like Hero's answer. Does anybody want to argue with Hero that that this is no good, that this is not the case? Or do we all think
So
that it can basically take any ship that floats?
so I would just maybe just to add to the statement. I mean, the boat is in it's kind of on a river, I guess, or something, but it's a river that's kind of not flowing, I guess. I mean, that's an interesting, maybe that's be a question too. What if the river has a current? Does that make any difference? But I think we're assuming that it's basically a very long lake that this boat is on. And then it's interesting to ask the question, how much extra load do you get on the bridge as a function of how long that lake is? If the lake were 10 times as long as the width of the bridge, could you then actually answer the question as to what the additional load is?
lost my club deck. I found it. I'm not super used to using club deck, so I lose my mute button occasionally. Yeah, we can, if we want, we can dive deeper. Do you want to dive deeper into that, John, or move on to the next one and loop back to it, depending on people's appetite? I was going to kind of gloss over all of them as they are and then loop back, see what people come back to in the discussions, which one captures their imagination the most.
That's fine. I'll say no more on that just now. I'll leave it to you.
Yeah, oh, that's cool. We can come back to that. It sounds interesting. So I think it's actually good to tease some additional juice out of each of these. Otherwise, we'll be through them pretty quick. So remember John's additional question about width versus length of the whole canal, not just the bridge. And we could come back to that. But let's go on to the second one, unless anyone's got any comments or questions. I think as a first analysis, I think I like Hero's answer that it doesn't matter how heavy the ship is because it's already carrying the mass of the water, and all the ship does is displace water equal to its mass. So yeah, any ship that's not dragging along the bottom can pass. Cool, I like that. All right, next one then. So this is slide number 3 down the bottom right of the slides. So fly versus train. This one firstly reminds me of a little joke. What's the last thing to go through a fly's mind when it hits your windshield? I'm sure you people know the answer.
I know.
You
Call
know
on me.
what's the answer? What's the answer, John?
It's asshole.
It's arse. Arse is indeed the last thing to go through its mind as it hits your window. So on that cheery note, and I know you're going to point out that my picture on slide 3 is a wasp, but hey, it's a pretty picture. That's all that matters. And it's probably also not taken in a train, but hey, who cares? So here I'll read out the problem verbatim. So a train travels at 100 miles an hour. A fly on a collision course travels at 5 miles an hour, exactly opposing the train. The fly hits the windshield and gets stuck. The fly continues to move with the train at 100 miles an hour. As the fly reversed its direction of movement, there must have been a point where it, i.e. the fly, had 0 speed just for an instant. If the fly had a speed of 0, then just for that instance, the train's speed must also have been 0. Explain how this strong fly could stop, even for an instant, a train travelling at 100 miles an hour. So that's an interesting one, bit of fun. Goes back to the topic we've been talking about quite a lot, John, recently, the C word. It's not as bad as it sounds, those in the audience. It's an innocent physicsy C word. But yeah, anybody apart from John, who's probably overqualified to answer it, want to answer either here or in the chat as well? How come this fly was going? If you're standing in the reference frame of the train track, you're looking at this event unfolding. The fly's going, let's say, left to right at 5 miles an hour. The train's going, say, right to left at 100 miles an hour. The fly must have reversed direction, right? It was firstly heading from your left to your right at 5 miles an hour, and then suddenly it's going to the left at 100 miles an hour. So it must have stopped for an instant. But it's attached to the train. So how did it stop the train? What's happening here? Let's have somebody answer who's not John to start.
How it is? Okay, I respect all of that, but how did you conclude that it stopped the train out of all of it?
Well,
Like
the fly must have stopped, and the fly's touching the train all the time, right? From the moment the fly hits the windscreen, it must be touching the windscreen, which is part of the train.
Yeah, it's touching the moving train all the time. It's
Yep.
stopping and then reversing.
Yes, but if it stopped relative to the tracks, as I stand there as an observer on the tracks and look at it, how come the train is still moving?
Because energy gets lost in different ways. I mean, you can make the same argument with a wall. So every time you're walking towards the wall and then you touch it.
So I don't like the energy gets lost in, well, maybe. I mean, energy getting
So
lost in...
there's deformation. It got deformed.
That's sounding more direct an answer. Although later I'm going to argue through a different problem from an energy standpoint, so I shouldn't argue against energy arguments. So tell me more about the deformation. That's sounding good.
Parts of that, what is it, the bug? So the bug has those particles, and those particles are all uniformly moving at 5 miles per hour. And then there's space between them all the time.
Yeah, let's
And
move
so
off the fly for a minute. I thought you were going to, just to stop you going down a funny alley, that the fly, however it's arranged, bits of the fly are in contact with the windscreen. So, and the windscreen's attached to the train. So how is that windscreen always doing 100 mile an hour in one direction when bits of the fly that are attached to it must have come to a halt at some point?
Because it depends on the moment. Can I say bad words?
Sure,
Depends
say
on
lots of
the
bad words.
momentum. So the
Later, you're
mass
going
of
to
the
be
fly
allowed to
is too
say
small.
centrifugal if you really want.
No, I'm not gonna do that. But it really depends on the mass of the fly and the mass of the windshield. And so
Okay,
if you want to
in what
look
way?
very
If we doubled
carefully,
them, in what way? If we doubled the mass of the fly, how would it qualitatively change the argument?
if you want to be very careful, it would change. But because the windshield will always be way heavier than twice, like two flies hitting the windshield at the same time, then it wouldn't make any difference. Like the distance that the windshield would react to the fly is only theoretical. This cannot be measured.
What do you mean the distance the windshield would react? Tell me more about that.
If
And by the way, if
if
anyone
there
wants to
were two
dive in and
trains,
help Shamash
if
out.
there were two trains, right, with the same mass and the same speed hitting each other, then
that'd be a bigger mass.
all of that energy would be translated into them jumping off the rails, and then the actual tension between the molecules being broken, right?
It's
So
all
you would
good.
see
It's
that
all good, but we need.
it's a big hit, right? It's a big
It's all
accident.
good, but we
Whereas between
still.
a fly and a train, the fly will be deformed. The train won't feel anything
But this
because the
train.
mass of the
Do
fly
you
is too
agree?
small.
Do you sort of agree in principle? But do you agree the fly came to a halt from the reference frame of the track? At some point, it was stationary. During its
From the
reversal.
reference frame of the track,
Yeah.
how do we
Start.
conclude that it had
Well, it
stopped
started
from the
doing
reference frame?
5 miles an hour right. Let's call that plus 5 miles an hour. And shortly after hitting the windscreen, it was doing minus 100 miles an hour. To get from plus 5 to minus 100, it must have passed through 0. And yet the train presumably didn't instantaneously stop, or did it?
Why are we linking the fly to the just because its head touched the windshield? From that moment onwards, it became part of the windshield?
Well, is that not your what? How do you?
No, but because if its head touched the windshield and its head started stopping, the back end of the fly is still moving at 5 miles per hour,
Yeah,
and
but
then
but
its back would hit the windshield.
just take a single atom from the fly's
Mhm.
head, if you like. Then tell
Yeah,
me about that single atom in the fly's head. Let's
that
not. It gets more confusing if we look at the billions and trillions of 10 to the however many atoms there are in a fly. Let's just look at one atom in the fly's head. How can that atom started traveling 5 mile an hour right and end up traveling 100 mile an hour left? It must have gone to a standstill. How come the train didn't?
I don't have an answer to that. If it's only
What do
one
you?
atom, and then it hit
You
the 100 mile an hour another atom moving in its direction, then at the moment of shock, if you only take a snapshot of that, you would never tell which direction the system is moving.
Okay, I'm gonna put you out your misery here because I think you basically have answered it, but by going into the complexities of how the fly deforms, it makes it a little more obscured. Anyone else want to give an answer before I give what I believe is a very simple answer?
Well,
We have
let me, because I think you're going in the same direction too. I guess it got me to thinking: is it really reasonable to say that when that first atom touches the windshield, right, that atom has to go from 5 miles per hour to negative 100 miles per hour? So there's a time when an atom that is literally in contact with the windshield is going at 0 miles per hour. What does that even mean for the atom itself to be doing that?
yeah.
Does an
So
atom deform?
so there you go. So for the first question, John's deeper question was about the width versus the length of the canal, and we can come back to that. If you want to come back to this question in more depth, then we can go a bit philosophical about what this means for the atom, John. That would be interesting. But let's again, for the sake of getting through all 5 and finding out what tantalizes people the most, let's just try and answer this one in a simple way. Shamash, in fairness, you kind of answered it, but then didn't quite double down on the simplicity of your response. My response would be that the windscreen, the part of the windscreen that the fly hits, does come to a halt relative to the tracks briefly. So the windscreen bends, deforms a tiny bit, that absorbs the impact and then rebounds and takes the fly off with it. So that's, I think, the simple answer is that the bit of the windscreen that it hits does deform enough to bring it to a complete halt relative to the track for an instant.
Yeah, but then what do you do with a single atom? Yeah.
Well,
Well,
that'll
that's
be
an
the
interest. That's an
that'll be the
interesting.
bonus. discussion. Yeah.
Yeah, well, that's an interesting thing, Ben, because I wasn't thinking of it that way, and I'm not sure I even believed that. But that really is interesting when you really talk about at the atomic scale what is going on there. That's a
Yeah,
tough
but at a
question.
macro, so atomic scale would be the bonus discussion, but at a macroscopic scale, I think that's a good first order answer. I'm pretty confident you did this with a piece of like plexiglass and a steel ball and a high speed camera. You would find that ball, well, the ball obviously would come to rest and it would be touching the glass as it does it, and therefore the glass is at rest. It's almost self evident that that's got to be the case, right? Macroscopically.
Well, so that means that you're really suggesting that an atom of the windshield is brought to rest from 100 miles per hour and then immediately rebounds back to 100 miles per hour.
Yep.
Yeah, I'm not sure I buy that, but I'm not sure I have a good argument against that. It's a really interesting thing to think about.
It's pretty. I think it's pretty hard to argue against because just imagine that high-speed film of the impact. You know that the ball or the fly is coming to a halt, and you know that it's touching the windscreen at the time that it does. Therefore, the windscreen's at a halt.
Well, let me try a quick argument against it. Suppose I travel along at a speed such that the fly suppose that I just move in a reference frame.
Or shall we do this as the follow-up, just to keep the whole like room at the same level of, so that we go through all the
Okay,
problems
yeah,
at a
that's fine.
cursory level. So I'm going to
Hmm.
write down on the slides what because each time you're coming up with a better bonus question. So let me just write this on slide 1. Bonus. How does length? I'm doing this for question 1, the water bridge. If you're wondering what I'm talking about, guys, look at the slide. How does length and width of entire canal affect this, if at all? Is that your question, John?
Yeah,
The
and let
bonus
me let
question.
me so let me suggest the bonus question for number 2 is, if you look at this entire process in a reference frame such that the fly was initially traveling at 52.5 miles per hour to the
Okay.
right and the train is moving at 52.5 miles per hour to the left, do you what is the what is the minimum speed of the windshield, right? is
Okay.
is it
Yep.
is it negative 50? But whatever,
Yeah.
anyway, that's
Yeah.
the
Yeah. Cool.
I
Okay.
don't
I've
know how
added
to
that in. Bonus. What does this look like from a frame where the fly was moving 52 miles per hour right, and everything else follows from that? Okay. Fantastic. Thanks,
right.
John. So just again to keep the level of abstraction the same all the way through, I'll go through all of them, see how we are for time, and then we'll go deeper. This is a breadth first search, is what we're doing here. Okay, so question 3. If you want the slides, they're linked at the top of the room. They're in the chat a while ago. I could even put them in the chat again for you if you really like, because I'm that kind of guy. Here you go, slides. Because depending on your device, it might be easier for you to click in the chat or whatever. Let me just have a quick look in the chat. If any of the other mods see anything in there that's cool, let me know. Yeah. No, not anything I can answer. I can't answer questions about John Denver's last hit, but I'm sure ChatGPT or Google can. All right, so here's another one. We've got a dude. It's called Swinging Balls because I like making up names that are slightly risque. And I'm just going to read it out as it says in the slides at the moment. So there's a dude swinging some balls above his head. Ignore gravity for this, as it says later on. It could be on the space station, strapped down in a seat if you like. Two identical masses, the black balls in the diagram, are connected by cords T1 and T2. Of equal length and swung around a fixed axis. So dude swinging a conker around his head, but that conker is attached further on to another conker. So a conker attached to a conker or something. If the tension in cord 1, T1, is given, what is the value of T2 compared to T1? Like as a fraction or a multiple of T1. Ignore gravity. I know that in
And I
reality, if
don't
you're on,
think people here know what a conker is.
well, a
It's a
conker is
chestnut, isn't it?
it's a chestnut, it's a walnut, it's a ball, it's a thing you hang off a string, right? So yes, sorry if I used an English term, but that is the language we're speaking. So no swearing. The word centrifugal counts as a swear word, but centripetal doesn't. I'm not actually that adverse to centrifugal, but we're going to try not to use it. You can if you want. Now explain your reasoning and the principles you used. And I would suggest you keep yourself out of trouble by ignoring the weight of the strings and ignore gravity as well. So, anyone want to have a stab at that? What is the tension in the string that you're holding if we know the tension in the other string? By the way, you could have like luggage scales in these strings, so they'd have to be massless luggage scales like those ones you get down the local physics store. But just a spring with a that's what I mean by the tension. If you had a luggage scale, the sort of thing you put in the middle of it, you lift up your bag with, what would it read?
So you're taking two equal masses and you're spinning them around each other.
Yeah, have a look at the
And the
diagram,
question
ideally.
is,
Yeah, try and look at the diagram if you can. I will also, if it helps people, I will try saving the image as well and putting it as my PTR, but don't rely on that because I might not be able to do that on the club deck quickly.
Ben, is the rope is one of the balls lagging behind at some point? Are they moving with the same angular velocity?
Yeah, good question, and let's assume they are. The system is accelerated up to speed, and we're going to ignore the wind resistance as well. So I'm going to add that as well. Ignore gravity and wind resistance. Yeah.
And I think maybe just to be clear, because Shamash's question might have been toward this, the second ball is attached to the first ball by
Yep.
its cord, right?
Yes, per the diagram, and the thing's spinning at a constant angular velocity, which also means a constant speed. We're going to ignore the weight of these strings. We're going to ignore any stretch in these strings. That's not what we're trying to get at here. What we're trying to get at is how centripetal forces work and how it varies with radius, just to give you a bit of
When the
a
time
hint.
comes, I have a bonus question.
Do you want to just type it straight in the slot?
Okay.
so
No,
just like
no, I'm kidding, but it's
at
awesome. It's
the
awesome.
level of specificity that's given, the outside one is traveling faster than the inside one,
Yep.
and therefore the delta V is greater.
Mm-hmm.
I suspect this is inverse square, although it may just be linear. Maybe it's linear.
Ben, I think
Yeah.
I think you need to modify your problem statement indeed before I even type my bonus question in the chat. You need to
Okay.
specify that they're being spun very quickly, that the spin is at high speed.
Why? Because of the gravity effect, which I said ignore, or because
Because
of
of
the
the
Yes.
tension in the rope,
Yeah,
so
so
that
I'm
it's the uniform.
let's just say it's being done on this International Space Station then, and the guy's strapped in his seat. We don't need to complicate it with the idea that gravity's pulling down and that this disk won't actually be horizontal. Just imagine it's being done in space. So I've put that in the question. Thanks, John. You're right, but it would complicate things a little bit
Is
more than
this
we want
the
to. Is this what? Go ahead. I think that was Joe. By the way, welcome to other people who've come into the room. We're doing physics
So
puzzles,
my
brain
final
teasers,
answer is
linked
that
at the
it's
top of the room.
linear. The relationship is linear.
Mm-hmm.
The longer the string,
The
the
relationship between
more
what and what is linear?
the length of the string,
Yep.
or the radius,
Yep.
and the velocity
Which
of
velocity?
the
The angular
ball.
or the linear velocity?
Well, the moment velocity of the ball,
The what?
the momentary velocity of the ball.
okay? So
Okay,
they
I don't
are
think that
identical
is.
masses.
I don't think that
Have
is
you
linear, by the way.
have you seen the simple
I know it is.
experiment where you use like a toilet paper roll and you put a string through it with a weight, and then you do this with a ball on the end and you spin it?
Yeah. Yes, I think so. Sorry, John, I muted you there because you're coughing, lovely as it was. It didn't add too
But
much.
isn't the no, it must be linear because the circumference of a circle is a multiple of the radius. That's what pi is.
Yeah,
So
but it
it's linear.
no. So what? So the let me give you the two formulas that are easy to remember. So the centripetal acceleration, you can do it two ways. You can say v squared. Now this v is the instantaneous tangential velocity you're talking about. Ben, if the string broke, this is the speed with which the ball would go flying off, right? So you can get the centripetal acceleration either as v squared over r, so that's the speed, the linear speed, the tangential speed, squared divided by the radius, or it's r omega squared. So now it's the radius times the angular velocity squared. Now, I prefer the second one for this problem because I don't want to think about the linear speed of these balls. I don't care because they're different. The linear speed of the two balls is different, right? So we're going to go to the other formula. Those two formulas are equivalent. which is r omega squared. And if you do that, you don't care what omega is, because it's just the angular velocity in radians per second. We don't care. And we don't care that it's squared either, because a constant thing squared is still a constant thing. So the omega squared bit we can ignore. So now we know that the centripetal acceleration, the acceleration towards the center of the circle, is proportional only to the radius of the string. And given that the masses are the same, we're a long way towards
But
solving the problem.
proportionality implies linear, doesn't it?
Yes, yes, it is, but it's not linear. You were purporting that the tension, which is the same statement really as the acceleration, is proportional to the linear velocity. It's not. It's proportional to the
Well,
linear velocity squared. It doesn't matter. It
the
doesn't matter.
velocity was linear to the radius.
The velocity is
The
linear to the
velocity is
radius.
linear to the radius.
Well, for a given angular speed, sure, but that's. I'm suggesting we want to try and look at this without worrying about what the
But you're
velocity
saying
actually
that the
is.
force is going to introduce an equation with a square in it? Is
The
force the relationship here that that force?
So
Oh,
for
boy.
a fixed rotational angular speed, so that's like RPM, revs per minute. Revs per minute can be directly translated to radians per second. So for a fixed number of revs per minute, if you double your radius, so you're on a roundabout and somebody's spinning it, right, and it's going around once every 3 seconds, let's say. If you double the radius of the roundabout, or you go twice as far out, it doubles the force you need to hold on. So it's linear. The radius has a linear relationship with the centripetal acceleration, or equivalently with the force you need to hold a given mass in that place. So that's what I just wanted to kind of give the hint and help out with. You kind of need to know that to do the problem, and I think we should ignore the linear velocities. The speed with which the thing's going round the circle in terms of the straight line speed that the ball would have if the string broke at that instant. So Shamash, maybe this is, so it's pure maths now. I've just told you that the
Oh
relationship
wait,
is.
I'm just not seeing where we jump out of linear and get to a different dimension. So where does that happen? John, can you help? Is that because the relationship between velocity and acceleration is jumps out of the
So
plane?
so I haven't been listening carefully, but I think you were correctly saying, Benjamin, that the velocities of the balls will be in proportion to the radius from the
Linearly,
axis,
linearly
linearly, right?
related to the
Linearly
radius, right?
proportional, I think. Well, linear
And
means
I think that
proportional,
Ben is
directly
saying,
proportional.
based on these formulas that he has, which he may have not derived, um, that eventually it's going to be a square, right? It's going to be a.
I don't
Uh,
think that's what he's saying, but I could be wrong.
he said it's not
Um,
linear, so I'm assuming
we
it's
have to
going to
be
be
clear about
square.
what there's several things going on here. You're thinking about velocity, but there's also acceleration maybe to consider, and then there's tension to consider.
So
So
my
all of those
question was
things,
this:
yeah.
if we go between velocity and acceleration, does that introduce a second dimension? Does that usually get us a squared function?
I don't know. I wouldn't want to say usually, right? In this case, I think Ben was saying properly that the easy, if you're interested in acceleration, which you should be in this case, then the easy relationship to use is that centripetal acceleration is the square of the angular velocity times radius. The reason being that they both have the same angular velocity. But you can use v squared over r, which is the one more people know, if you use what you just said. If you know that velocity is proportional to radius, right? I think that's what you were saying. Then you can use
Yeah, I
that one
guess I'm just
too.
curious how do we get from a linear to a
So
planar
but without going
math
into
here? That's
so we don't lose the wood for the trees. If you just grab yourself a bit of paper, and you can do this algebra really quickly, right? Note that v, if we're going to say that acceleration is v squared over r as a starting point, for example. Now, how you can derive that as a separate question. We can keep going back to the beginning of the universe, but let's start with v squared over r. Seems to be the one you're more comfortable with. It's the centripetal acceleration. You can now note that that v is a linear speed, so you know how far it goes around a circle, 2 pi r. Yeah, and then you can do the substitution and say that speed is distance over time, and now you can work out how long it takes to go around a circle. you can and you can translate all that over to radians per second. There are 2 pi radians in a circle, and it's just a little bit of algebra to go from acceleration equals v squared over r, which is also equal to r omega squared, or omega squared r, where omega is the angular acceleration in radians per second. You'll find that's all dimensionally correct, and if you do the algebra, you'll find it works out. But let's not go through that. That can be the bonus, unless John's got a better bonus. But I'll put that in as one of the bonuses. I'm going to say bonus 1, how do we derive A equals r omega squared? We'll put that in as bonus question 1. If John wants a second bonus question, we can
I
have it.
I actually beat you to it. So I just said bonus question. So your question 1 is the second bonus question on this.
Oh, okay. Have you already put that in?
I did. And
Oh,
not
okay, that's
that.
weird.
You can read my bonus question. It's in there.
It
It's
hasn't updated.
complicated. Mine's tough. Mine is really tough.
Well, my Google slide hasn't updated, which is weird, John. So I hope we're on the same slide. And I've refreshed.
I'm sorry. I just put mine in the chat.
Oh,
Sorry.
you
I
put it
thought
in the
that's what
chat.
you.
Okay,
Yeah,
that's
yeah.
cool. Okay, and by the way, could one of the other mods have a look in the chat for me and try and tell me if there's anything I should be aware of? Because
Yeah, well,
Wisdom is
just got.
commenting on the glass, yeah.
on the glass. Oh, you mean with the
Um,
train?
but
The earlier problem.
he's making it sound really complicated and physicky, you know?
Okay, well, let's come back to Wissam when we go back, if and when we go back to that question. So I'm going to put, okay, I'll put speaker notes in that says Wissam's question. Cool, thank you. All right, so let's just finish this one then, because we still haven't got an answer. I'm going to challenge Shamash to give you me an answer. Shamash, the tension is proportional to the radius.
Yeah. And
Okay,
the
so
radius is multiplied by 2 because they are equal distance.
Yep, so what is T1 in terms of T2? Or the other way around, what is T2 in terms of T1?
So T2 should be twice T1 if it's proportional to the radius.
You sure?
I mean, looks like it.
Okay. But T2, so look, T1, if the inner ball wasn't there, T1 would still be T1. Do you agree with that?
No, because you're losing mass, and
You
so
sure? So if the inner ball wasn't
when
there,
when you lose
how would the
mass from
outer
the first ball, the tension should change, no?
T1, the tension between the inner ball and the outer ball, if you took the inner ball away, would the outer ball know anything about it?
I have the wrong notation. Hold up.
Yeah.
So
T1's
T2
the
is the one
outer.
inside.
Yeah,
And
T2
then
is the one
T2 is the
inside.
one outside. Yeah, okay,
Yeah.
come again.
So if you take away the inner ball, does the outer ball have any notion of that? Does it care whether it's attached to a ball in the middle of a string or just to a bit of string?
No.
It doesn't care. Okay, so T1 is going to be what it is regardless, and we're just calling it T1. Whatever value it is, we're calling it T1. Okay, how big is, so ignore T1 for a minute, how big is T2? Well, how much tension do you need just to swing the inner ball if the outer ball wasn't there?
Some number.
Yeah, but what is it as a proportion of T1? If we said it's linear with the radius, it's proportional.
Okay, so once T1 is given, so T2 should be half of T1?
Yes, correct. Now, what's the total tension in that string at T2, though, between the hand and the first ball? Because you've got to have the tension.
Sorry.
So you've just told me what the tension would be if there was just the inner ball. You said it was half of T1, but we've also got the tension of T1, right? We've still got to support the outer ball. So what's the total tension T2?
It will become T1 plus half itself.
Yep, which is?
Which is 3 over 2, 1.5 T1.
Good job. Okay, that's the answer. So the answer is T2
correct.
is 1.5 times T1. Okay, assuming all the things we've assumed. And we have two
Hey, and now
bonuses.
I have to concede too that because I made a conceptual error in not including the T2 and T1. So my bonus question was bogus. It was a bogus question, not a bonus question.
Well, I'll just delete it then. Well, I mean, yeah, because bonus question 2 is bogus because we're ignoring gravity because it just makes things slippery. Okay, cool. So in the spirit of going through these again, we're doing what I call a breadth first search. If you wonder what that means, by the way, imagine you're trying to find every leaf on a literal tree. I'm out in the garden now looking at trees. There's a few ways. You could go depth first. You could go up the trunk, down a big branch, down the next branch off that. and you could go all the way to a leaf and then back up one and go to another leaf and back up one and go to another leaf, and you'd end up exploring all of the leaves on one of the major trunks before you move to the next major trunk, right? That is a depth first search. A breadth first search would be you go and find all the trunks first. You go down the main trunk and you find all the major branches off it. And you say, okay, I've found all the major branches, and I'm now going to go one at a time down each of the major branches and find just one more level of each of them. Now, it'll take you ages to get to the leaves, but you see the bigger picture of the tree, right? We're doing that. We're doing a breadth first search. So when we're getting like deep questions about, oh, the details of this leaf, we're saying, hold on, that rabbit hole is never ending. Let's decide to stay at this level of abstraction for now and be disciplined and see the whole tree, all of the major trunks off the tree first, before we decide which leaf is most interesting. Because if you find a pink trunk, you can be pretty damn sure that's a weird freaking tree, and that's the major branch I want to look at. Otherwise, we could spend all our lives looking at boring green leaves. So that's what I'm doing here, and trying to make sure that it keeps the flow of the room on track. So we're going to move on with everyone's permission to number 4, and we'll go. We'll go on from there, and then we'll come back to like Wissam's discussions, etc. We'll see which of these is the hottest topic. And on the topic of hotness, we have puzzle 4: under pressure. A solid cube rests on a level surface. The cube is heated by a large amount. Does the pressure the cube exerts on the surface increase, remain the same, or decrease? Answers in the chat: A, B, or C, or increase, same, or decrease. Now, ignore relativistic effects. This is recommended. If you want to include relativistic effects, then be prepared to quantify them. Hint, I wouldn't bother, but if you want to, then you need to talk about stuff such as specific heat capacity and E equals mc squared, and do those numbers properly to convince me that the thermal effects swing the argument in the other direction. I think they won't. When I say heated by a large amount, I mean hundreds of degrees C, not stupid amounts, right? So I'm talking about the temperatures that everyday materials can withstand. So let's avoid the whole relativistic discussion before we have any smart asses come up with that. And let's just keep things really simple again. Breadth first search. What does the pressure, the cube of practically any material you can imagine, do as you heat it up?
Do I take it that you're phase changing the cube?
No phase change. Good point.
No phase change.
Wait,
Yeah.
I can't see the slide. So are you saying does the pressure change or does the like total force change?
Well, I'm asking about the pressure.
Ooh,
By
I know
adding
where Andy's
heat,
going.
by adding heat that's not phase changing. So the surface area doesn't change at all of the cube.
How can you justify the surface area doesn't change? How do we know the surface
You said
area
it's not phase changing.
I said it's not phase changing, it's not melting, for example. But if I heat a block of metal, does it stay the same size?
Thermal expansion is in play.
It is indeed. Let's assume that thermal
I
expansion
didn't realize
is in
that's where
play.
you were going with this. That's pretty cool.
Yep, just keeping it, again, breadth first, John, keeping it simple.
So the pressure would go down because the surface area goes up.
Give that man a banana even though he's driving. Is it safe to eat a banana while you're driving, Hero?
I might flip, but it'll be hilarious.
Yeah, so that is...
I did not see that one coming. I thought you were going somewhere else. Yep.
No, just keeping it simple. Just keeping it simple.
And I thought
So,
Andy was going to ask, is this a compressible cube?
so all I'm trying to get at here is when you heat shit up, it gets bigger, typically, nearly everything, because things move around faster, and therefore it jiggles more. And...
Except for ice takes more space than water.
Yes, ice does. Ice is extremely unusual in that, by the way.
And that's one of the most magical things that keeps our world going, because otherwise you wouldn't have turnover of nutrients from summer to winter.
I'm not even
Inside
sure you'd have
lakes.
oceans. I think they might freeze from the bottom up if water sunk, but luckily it doesn't. And obviously the reason ice floats, if ice sunk, the reason ice floats, of course, is the way that the molecules arrange themselves in a solid versus a liquid version of water. And it's a bit unusual, that. And it was a very good point, Joe, to bring up phase change, which is why we said we're not talking about it melting. Even though my image I got from stock media is an ice cube on fire, which is a crazy crazy concept. Yeah, we're not talking about that. We're just very simply saying you take most things, you
Yeah,
heat
I
them up,
saw that
they
thing and I saw
expand.
ice and I was like, wait,
Yeah,
your
yeah.
pressure is going to be decreasing because you're going to be phase changing and you're going to have less mass in the cube in the first place.
All valid, very valid points, yeah. But again, the simple take home here is when things get hot, they expand. And those forces involved in that can be astronomical at times. So, and things also expand with a lot of force when they get wet, of course, but that's a topic for another day. So that again was very simple. John, do you have a bonus for this? For if we have time to come back, we may not have time to come back to any of these bonuses, depending on how we
Well,
do
I
the
will
voting.
just say that I think I can quantify the relativistic correction, but I mean, but I wouldn't try to other than to just say it. It's probably worth saying at some point. We don't have to say it
Well,
yet.
yeah, well, I think it's just. I think it's quite simple, isn't it, to do that, John? You just need the specific heat capacity and equals mc squared, right, and rearrange that.
Do you need the
Right.
volume of the ice cube as well?
Not to say qualitatively whether the pressure will increase or decrease. If you want to quantify it, then you may or may not need the volume. You need that would be another good bonus question. What drops out of here in terms of scaling factors? That would be another good bonus question. Quantifying it would, in general, be a good bonus. John, do you have a suggested bonus? I'll put something in as a bonus.
I don't think I do.
Okay. But let's say my bonus would be quantify this for a pure iron cube heated through, no, I'm going to say from a particular temperature to a particular temperature, from 20 to 200 Celsius or something at standard temperature and pressure. That sort of thing would be a bonus, right? I want to know how much a pure iron cube, is going to expand when heated from 20 to 200 Celsius at standard temperature and pressure. And then from there, you could work out, and it's a cube, so it's all proportional, you could work out the pressure drop. But that's a bonus, and let's move on. We've been going an hour, and we've got about half an hour to go. Hero, go ahead, buddy.
Well, I was thinking, um, is it possible to have a material that shrinks as that has a negative coefficient? What do you call that?
Like temperature coefficient of expansion.
Thermal.
That's
Yeah, yeah. Is
yeah.
it possible for material to shrink when it warms up? Not
If you're phase
involving
changing.
a phase change.
Without a
Not
phase
involving a
change.
phase change. Yeah, yeah,
Well, I think doesn't
yeah.
rubber do that? I think rubber may do that.
It goes back to my question the other day about is it possible to have a material that expands when you put more pressure on it?
Well, there is. I mean,
kind of get why that might not be true.
sand does that, Hero. When you walk on the beach, the reason it looks like the sand dries out around your foot is because it's expanding when you put pressure on it because of the way that the packing changes. It's to do with the way that the faces of the packing of the sand, the ball packing of the sand, that is possible within reason. But you don't get what you don't get is a perpetual energy machine. You don't get free energy from that. But things can expand when you force them.
So
If
wait,
you have
what? I don't understand this sand thing.
if you have a bottle, let's say, full of sand and water, and then you imagine that, John, and then you have coming out of the bottle, say the bottle is horizontal, and coming out of the bottle you have a straw with and you have some water in the bottle, and the water level goes halfway up the straw, right? So the bottle's just sitting there, full of water and sand. Sand's all packed in, and the straw kind of goes out of the bottle to the right and up, and then it has water in it. So you can see the water level in the whole system. If you stand on that bottle, the water will drop in the straw, which is kind of crazy. And it's because the
That
sand
is.
it's kind of the sand rearranges itself under force, and that's the reason that sand does what it does when you walk on a beach. Now I can substantiate this with I'll do something like find you a YouTube video of it in a few minutes. I'm trying to run the room, but I'll do it in a few minutes, and then you guys can look at that as an extra bonus. That's quite fun. In fact, I'll get you that now, and then we'll. Okay, here's one, I think. Let me just see if this is any good. No, that's not a good video. Give me a few minutes to get you a good video, because I don't want to get you a crap video.
So does it have to be wet sand? Is that what you're saying?
Yes, yeah, it does. Yeah. Let me find that as homework in a few minutes rather than rushing it now, if you don't mind. Because otherwise I'll get you. Oh no, here you go. No, hang on 1 second, sorry. I will just do it now. Okay, this will do. This Action Lab video I'm about to put in the chat will serve the purpose. Wet sand expanding under. Good point, Andy. Thanks everybody. But between Andy and Joe and everybody, we've got some really interesting contributions. There is in the chat just now a YouTube video from a source that is pretty good, which goes into that in more detail. But Brett, first, let's do the last one and then see how we get on and what tantalizes people to talk about more. I've only got about half an hour more to run, so I want to make sure I get through all the questions.
Wait, did we consider the possibility that it increases the pressure?
Did we consider what possibility then?
The possibility that the cube increases the pressure.
Not really. We're just saying in general, most things without phase change expand when they get hotter. In most cases, I'm not saying all things in all cases. I think you can have negative thermal expansion in some alloys, some crystals, possibly silicon. I don't know. There's a few things that come to mind that I think might do that. But we're saying that this is if you pick an object at random, a material at random, it's going to expand. And it's just simply saying if it expands, then it's a bigger area.
Include glass.
You might.
Yeah,
That's
silicon,
very close to silicon.
glass is an example where you might be able to shrink the distance between bonds.
Yeah, you might well be right.
And that's because glass it's a polymer.
Now I'm just going to move to somewhere
So
else.
I calculated the expansion for diamond to be in the neighborhood of 0.02%.
Yeah, small values.
Pretty small. But I was thinking that the interaction with the air above would be aggravated by the temperature. So every molecule hitting that surface would be accelerated, would be bounced back with acceleration. And the additional acceleration of those excited air molecules would produce topside pressure, and that topside pressure would translate to bottom side pressure.
Not really buying it, but maybe for the bonus discussion. The simple take home, again, not to lose the wood for the trees or the trunks of the tree for the leaves, is that most things when you heat them get bigger. As simple as that. Of course, there's always infinitely deep discussions you can have about anything, and actually it never ends, and then it ends up in philosophy, and then I commit hairy-carry. So we're going to go on to number 5, which is confusingly on slide number 6, which is called bootstrapping. Now the idea of bootstrapping, we use it in computing. That's when you boot a computer. That comes from the term bootstrapping. That's the idea that how do you get a computer running when it's off? It needs to pull itself up by the bootstraps. It needs to start itself from nothing. Now, clearly, you can't lift yourself off the floor by pulling on your own feet. That's silly. They're all internal forces to yourself. But that's the concept of bootstrapping. And here's a thing. You're sat on a chair, or you just have a rope around your waist, let's say. That rope goes up in the air over a pulley and back down to you. So you can. Now, can you pull yourself up in that way? So let me read the question out verbatim, and then we'll discuss it. So consider the system shown on slide 6. It's just a dude in a chair, or could just have the rope around his waist. Rope goes up in the air over a pulley and down into that person's hands. So a lightweight chair is used with an overhead pulley. Can a person lift themselves? Assume the pulley is frictionless and the rope and the chair's mass are negligible. For example, the rope, it's a light rope and it's tied around your waist. If you can't pull yourself up, why can't you do it? And if so, how much force do you need to exert? Let me put you out your misery. You can pull yourself up. I know this because I did it. I did this. I scared the shit out of actually, firstly my father and then myself. I'm not sure who got scared first. I think it was first my dad and then me. There was an old scaffolding outside a building in London, and his flat's on the 3rd floor. And there was a bucket that the builders used to take stuff up and down the scaffolding, literally a waste bucket, you know. And it was big enough for me to get in, especially as a kid. So I got myself in the bucket and pulled myself up to the 3rd floor window in the bucket and tapped on the window. And my dad came to the window and shat himself because I'm there just like holding onto this rope. And I was quite smug about it until I started to realize it was actually getting my grip was getting a bit sore. So me and my dad lowered myself back down. I probably could have lowered myself back down, but with typical teenage stupidity, I hadn't really thought about what happens if I get tired at the top. So anyway, I've done this. You can pull yourself up, so you can ignore that part of the question. The question really becomes, how much force do you need to exert pulling down on that rope? And how do we know what that force is without going into force diagrams, free body diagrams, any of that stuff? There's another way we can find out what that force is. And as a hint, you can think about it through an energy lens or perspective. So discuss how much force do you need to pull down on that rope to pull yourself up with a pulley?
Well, I would say you need. You're not gaining anything here. In other words, you have to pull with the force of your own weight. I mean, we're assuming
Half
friction
of
is
the
right.
weight.
So that you're
Okay.
not gaining anything I liked a lot, but maybe back up one. And I was going to ask you to qualify not gaining anything through which lens?
Well,
What law of physics says we're not gaining anything?
Well, this is the way I would think about it. To gain a foot, you have to pull a foot of rope. So there's no mechanical advantage.
Do you?
To gain a foot, you have to pull, what, 2 feet of rope?
The question
Andy,
is, what does it mean to pull a foot of rope? What does that mean?
Well, so if you were at the bottom and you had and the pulley was 10 feet above you, how much rope is there in total from your hand?
Oh, wait a minute. I could be wrong about this. Oh, it's a moving block. This is what we call a cascade. All right, actually, I retract that. I think.
Okay,
I'm gonna have to
that's
pull
fine.
over. I'm gonna have to pull my car over and think about it.
It was sounding really good. You don't get a free lunch, you started to say, and I liked that. And then if we think that if the distance from the person to the pulley is, say, whatever distance, 10 feet, 100 feet, don't care. Let's make it 30 feet, like my case when I actually did this. Then there's 60 foot of rope, right? Rope's got to go up and back. And if I pull all that rope through, I must have pulled all 60 foot through because suddenly there's no rope left between my hand. It's just my hand to the pulley to my waist. So just to say that and let you or anybody else carry on.
Yeah, so the thing if you're standing on the ground and lifting a thing off the ground, then that's what I was saying would be true. But since you're moving up with the thing, yeah, you're pulling twice as much rope. So it's like if you're pulling twice as much rope and going, then the distance you move, then just the amount of work you're doing.
And as you're moving up, each
this is
segment of tension is half the total mass.
I'm liking these halves I'm hearing from Joe and Benjamin, and I'm nearly 100% liking Hiro's argument, but just tie it together, Hiro. So you mentioned work. Keep going. So you've identified correctly that you need to pull twice as much rope as the height.
Oh, how about this? Work is force times distance. If effectively you've gone twice the distance, you must be applying half the force because the work has got to be this. The work is getting the thing to the top. If you've pulled twice as, whether you lift it to the top or whether you pull twice as much rope to the top, the amount of work done is the same. The amount of work done must be the same. So the thing that changes in any pulley system is how much rope you pull compared to how much distance the thing has moved.
I like that a lot. I think that's another banana. You're going to be too fat to get out of that car soon. Yeah. So I like that a lot. Anybody want to argue?
I say it's the same force.
Okay. So
it strikes me that there's an element of this which is similar to the question of whether running on an inclined treadmill is the same thing as running up a hill. And I'm thinking about it in terms of, so imagine that you pull, so relative to the ground, right? Somebody's standing there and they see your hand go down 1 foot. Then your body, then what does your body do? What do they see your body do if they see your hand go down by 1 foot?
Your body has to
So
go up 1 foot here.
I think your
But
body
there's
has to go up
something
by 1
counter.
foot,
Yeah, I'm
but
not
so
and what
convinced.
so
and how much does your center of mass go up when you do
so
that?
before we go
Wait,
into
what was the what
the
is the starting premise?
so before we go into the depth, I think we've got a bonus discussion here. I think we've got our first analysis answer, right? Which is that you have to pull with half your weight, and that
Yes,
can
you
be
have to
derived
pull with
purely
half your
from
weight. But the
purely
bonus
from
question is
conservation
whether or
of
not
energy.
it's the same amount of work. That would be the bonus question
Well,
for
and
me.
here's the other question.
It's not the
Well,
bonus question.
How hard do
what
you have to pull to just sit there?
Also half your weight.
Yeah, so and this is where it becomes like the running on the incline treadmill. You have to get yourself started if you want to move up. And to do that, you have to pull with more than half your weight.
Yeah, but only
Half your weight in a gram.
yeah, only a you know, you don't need to accelerate very much. So yes, of course you do.
That's right. But
That,
then after that, how much work are you doing? Well, you're doing the same amount of work in some sense that you were doing and you were just sitting there because you're pulling. Well, you're not the same amount of work, I guess,
no,
but
because
this
yeah,
is where
it's
it gets tricky, right? Because the force that you have to apply as you're raising yourself is exactly the same as the force that you have to apply to just sit there.
it is, but but when you're just sitting there, no work is being done because that force is moving through no distance in the direction of the
Well, that
force.
depends on your reference frame, doesn't it?
The reference frame of the person in the chair. So from the reference frame of the chair, the energy you exert is the force you're pulling, which is half your weight, times the distance that you pull, which is clearly the length of rope you're consuming, which is I think it's as simple as that.
Sorry, I still don't understand why would
On
it
the
be half
first
the force.
analysis.
I still
Well,
don't understand why would it be half the force, because
Oh, well,
if there was a
so
person who weighs 50 kilograms and another one weighing 51, the 51 one will drop. So
well,
if
it's
so
not
so I
two
think the
people.
important thing there is just under, yeah, you got two ropes attached to you. Both of them are pulling you up. One is attached to you through the chair, and one's attached to you to your hand, right? But they both exert an upward force on you.
that upward force must be equal because the pulley's frictionless, and if it, I mean, if the pulley's going at a constant speed, so Shamash, to imagine why it's half the force, the way that the shortcut we've taken here is to look at the energy of it, right? If you were so let's take the situation where I'm on the ground pulling somebody else up. I have to the amount of gravitational potential energy, which is the only thing we really care about. Yes, they get a little bit of speed and kinetic energy, but we don't really care about that. But I can pull them up as slowly as I like. The amount of gravitational potential energy they gain is their mass m times the gravitational acceleration g times the height through which you pull them, h, mgh, mass in kilograms, g, 9.8-ish meters per square second, h in meters, right? That gives you the literal amount of gain in gravitational potential energy in a uniform gravitational field for a height h in meters. And it gives you that in joules. Fine. Now, you don't get a free lunch, which was one of the first things that Andy said, which I really liked. So if you're sitting, instead of somebody else pulling you up, you're now pulling yourself up. You don't get a free lunch. You have to do the same amount of work as the person on the outside. But you get to pull the rope through twice as far. So force is so one way of looking at work when you're pulling on, say, a rope is force times distance moved, right? So force in newtons times distance in meters gives you work, gives you joules. So because compared to the person pulling you up from the ground, you're pulling the rope through with twice the distance moved, it must be half the force because the work is equal. Does that make sense?
yeah, I had a conceptual mistake that I drew the force, one of them upwards, one of them downwards. They're supposed to be twice up, and because I'm
Yeah.
holding both ends of the rope, yeah, that makes
Yeah, that
total
can
sense.
happen. And that's why I wanted to analyze this problem through the lens of gravitational potential energy rather than getting stuck in force diagrams, which can be great and can be very general. but often you can circumvent those sort of things by switching to the right argument frame. In physics problems in general, you can really do well by spending extra time considering a few things, like symmetry of the situation. Is this cylindrically symmetric or linearly, or you know, is it like mirror symmetry, or do we have a spherical type of symmetry to the whatever? Considering the coordinate system and the symmetry is a classic one. Considering the system boundaries, where am I going to consider the boundaries of the system? Considering whether it can be solved by purely, for example, through an energy or a momentum type of argument. There's a lot of tricks like that you can do, which can make the problem much simpler. And that's what I was kind of getting at here. I don't know if I have a bonus for this one, or indeed if we even have time for bonuses today. I've got 18 minutes to go. But I thought that was a fun one. Anyone want to suggest a bonus question? And then we'll recap the questions and see what we want to talk about.
Well, the thing I was thinking
I
about
want
was,
to challenge
Oh, hold on.
the
Hold on,
assertion that
Benjamin.
it's the
Let's
same
just.
amount of work.
Okay, well, you can do that. So you can do that in a minute. Let's hear Andy, because he's quieter, and then I'll come back to you, Benjamin, on the challenging the assertion.
yeah. Well, I was going to make, so one way to think about this is sort of flip it around, like try to come up with an equivalent system that's just a little different. So an equivalent system would be, instead of you're pulling yourself up on a chair, how about you're up at a height and you're like lifting a bucket. If you just had a line, or down and attached to the bucket, you would have to lift with the whole weight of the bucket. If the line went down and threw a block and came back up, and so the rope's attached to you and then goes down and through a block and back up, and you pulled with that free end, I think that would be really, most people would see that right away and be like, oh, that's half the weight. I'd be pulling with half the force necessary to lift the bucket. I got to pull twice as much rope. But it's exactly the same problem. It's just it's just flipping it around a little bit. The thing that makes this tricky is that like you're the one moving, but you can kind of change reference systems and come up with an equivalent system that's a little more intuitive, I think.
Yeah, and I've got a very funny video to share with you guys at some point. It's a health and safety briefing about some idiot on a rope on the side of a building. And I think it might be a real idiot actually getting slightly hurt. I hope they're okay. If I can find it, I'll put it in the chat as I did the last one as promised, but I can't yet find it. Benjamin, I've taken your objection as a bonus. I've written it in as a bonus question, so thank you for that. So I think what we'll do now is we've got 15 minutes to go. Let's just recap the few questions we've had for anybody who's late, etc. And then in any remaining time we can have discussion. And then if I run out of time, which I will in 15 minutes, I will hand over to, if John and Shamash and others want to run the room, of course, well, it's John's room really. I'm just a hanger on here trying to keep the show going while in John's absence trying to fumble my way through. So thank you for still being here when it's not the genuine article. This is like when a, what do you call it, a support band or whatever comes on. What do you call those bands that come out first? They've got what's the name of a band that comes on before the main band? Come on, help me out, people. John.
Warm-up.
The warm-up band.
That's what you call an opening act.
In the opening act, the warm-up band. This is like a warm-up band that stayed for the whole bloody show. So thank you for those who've hung around. So let's just quickly go through the 5 problems, and then I'll tell you what the bonus questions are, and the purpose of this is to see if we want to discuss. We probably only have time to discuss one of these. So question 1 was a water bridge. Here's a bridge. The bridge contains water. It's a canal going over something. It's on slide 2. And the question is, if a boat, how heavy a boat can actually cross this bridge? Is there a weight limit when you have a water bridge? So a boat is floating across a bridge that's carrying water. The answer was there is no weight limit. As long as the boat stays floating, it doesn't matter how heavy the boat is, because the boat will just displace its own water. And the bonus question is this always true? Does it matter how thin the canal is, how long the canal is, either off the bridge and on the bridge? When does this fall apart, this assumption? And do we want to go into further discussion of that? So that was puzzle 1, the water bridge. Puzzle 2 was fly versus train. It started with the joke, what's the last thing to go through a fly's mind when it hits your windshield? And of course, John got the answer right there. It's his arse is the last thing to go through its mind when it hits your windshield. And the question was this: a fly is heading towards a train. Basically, a train hits a fly. The fly was going, let's say, left to right to start with at 5 miles an hour. The train was going right to left at 100 miles an hour, so they were both heading towards each other. But very soon after the collision, the fly ends up going right to left at 100 miles an hour with the train. But that means the fly must have stopped, because initially the fly was going, from the perspective of somebody from the outside, the fly was going in one direction, then it was going another. If the fly stopped and it was attached to the train must have stopped. What's going on? And John's bonus question here is, what does this look like if you took a different frame? And he can explain that if we decide this is the one that's most fun to talk about. Number 3 was swinging. Just vote in the chat about which one you want to talk about, or just have a free-form discussion. Number 3 was about swinging balls. You were swinging 2 balls above your head. Really best to look at the slide here. And this was about the tension in the string. I don't think this is going to be the bonus one, but we can do. And the bonus question was, how do we know what these formulas for centripetal acceleration are? Where do we get them from? How do they work, etc. They're not too tricky, but we could talk about that. Puzzle 4 was just heating something like a cube of metal on a surface and saying what happens to the pressure the cube exerts on the surface as it gets hotter. And what I was getting at is the fact that most materials expand when they get hotter, and if it expands, it gets bigger, and if it's bigger for the same weight, the pressure's lower. But there's a lot of other things. We could go and quantify this, so like, get a real value. Is it like 1% lower or a fraction of a percent? So that would be the bonus question there if we wanted to. And the final one was what we just discussed, which was pulling yourself up on a pulley. Like up a building site, like bucket on a building site or something like that, which I've done, and it is a bit scary and it's quite fun. It's easy. Well, it's as easy as the physics says it is. You pull with half your weight, but don't forget you get tired, and if you get too tired, you're going to get screwed. So I'm glad my dad was there to help me down. And the bonus question there would be from Benjamin, which is how much work is needed, as in energy, as in how many Mars bars do you need to eat? If you do it, you pull yourself up versus you pull somebody else up. Is it the same? Given the assumptions of the question, or is it not the same, and why? So there you go. They're the 5 questions. I'm going to shut up and eat the beautiful snack my wife has just put next to me, and happy to hear any discussion. Mods, you're welcome to bring other people up, and I'm going to disappear in 12 minutes promptly for dinner, but happy to be here till then and leave the room running until everyone's bored of it. So thanks for listening, everybody, and I'll just listen into the discussion now while I eat my snack.
I vote for the boat one, the first one.
Okay, and other people can vote in either voice or in the chat. Okay, so I want to eat this, whatever it is, bean curd rice and soy sauce thing. So here, if I can put it on Hero, John, Shamash. Oh, John's gone. No, he hasn't. To keep the conversation going. Benjamin, he's always good at keeping the conversation going. Keep it going for at least a couple of minutes while I stuff my face. That'd be amazing.
Okay, well, it's my job to keep the conversation going. I was going to just say that different sources of energy have different kinds of efficiency, which leads to certain speeds being more efficient than other speeds. And I think that it's the case even with people, that exerting work at a certain rate is comfortable, and exerting work at a higher rate is uncomfortable because it's inefficient. And that's why doing things where the resistance is sort of optimal is preferable. And that's the case for bicycles and trains and rocket ships, that there's an ideal relationship based on efficiency. Therefore, it's more work to do things inefficiently.
That is definitely true. Just a few days ago, my daughter, who's a CrossFitter, well, we both are, was on the exercise bike we have here, and it's a Concept 2 bike, like a Concept 2 rower, and it has a thing that determines how much air can flow. So you have a resistance, as you say, Ben. And we're doing zone 2 training, so it's constant cardiac output, 120 beats per minute pulse, very low pulse. And what we were plotting on a chart is the number of watts of power we're producing versus the resistance level set, and you get exactly what you suggest. If it's too easy, the bike's in too low a gear effectively, your legs are spinning really fast, then we're not getting so much power output. We're maybe getting 80 watts for 120 beats a minute. And if the resistance is too high, you're also not getting the best power output, and it peaks, actually in our case, both of us, somewhere in the middle. So very much the case with humans. In fact, it's worse than that with humans, that humans need to actually waste energy to hold something. It's kind of stupid. If I give you a 50-kilogram medicine ball and say, here, Ben, hold this, mate, and come back an hour later, you're going to be pissed off and sweating and have used a lot of energy to hold that ball. But if I put that medicine ball on a table, the table was perfectly all right for 100 years and uses no energy holding it. So from a basic physics point of view, you shouldn't need any energy just to hold something, but human bodies do, because our muscles are certainly non-smooth muscles. So most of the skeletal muscles are not something called smooth muscle. They need to keep refiring just to keep a force. So it is exhausting. It is exhausting just doing nothing, just holding something in place, where the first analysis physics says it shouldn't take any energy. So that's a good point.
So for problem 5, I'm imagining if you hold one ends of the rope with your hands and you have your feet tied up to the other ends of the rope. For some reason, my intuition is a lot more at peace with that picture, because as you pull with your hands, you will always be perfectly horizontal. I don't know.
Sorry, Shamash, I'm afraid I slightly tuned out there because I had to tell my wife when the room ends and stuff. So just restate, you said something about being horizontal and feet and hands.
Yeah. So if you imagine for the same problem, instead of you sitting down, if you imagine removing the chair altogether, having your feet tied up to the rope, and holding the other end of the rope with both of your hands and trying to pull on the rope with your hands, my intuition, for some stupid reason, is a lot more at peace with that picture, because now I'm pretty certain that you will always remain horizontal as you pull on that rope with your hands.
Horizontal. Do you mean vertical?
No, if you start at a horizontal position.
Oh,
right?
okay. Oh, well, tricky.
Assuming that your body is uniform, right? It's not like your head is heavier than your hands or whatever.
That'd be a really
Assuming that.
awkward way to do it, though.
Yeah, totally.
I was thinking you meant vertical. I mean, you can grip a rope with your feet. When we climb ropes in CrossFit, we do that. You have to have special shoes, otherwise they just get wrecked on the way down. But you lock your feet, you lock the rope between your feet, basically. It's a bit of a weird motion. And then you mainly push yourself up the rope with your, if that's what's prescribed. Sometimes it's prescribed to not touch the rope with your feet. But you can certainly lock your feet on a rope. And then if that rope went over a pulley and back down, you could certainly pull yourself up the other rope. So while staying vertical, you could do that. You would have to be careful. I'd want the rope that's coming down to go inside my arms, if you like near my chest, because you would flip upside down really quickly. And if you did flip upside down, you would lose grip on it from a pragmatic point of view. But yeah, I mean, I would rather just do it vertically if I was going to do that. You certainly could do that. You just have to be careful that you don't end up going horizontal. But yeah, cool. Anyway, so whatever, let's just chat about it. I'm cool. Inviting Kumar, Kumar up on stage.
Yeah. Anyone else?
It's been fun. Thank you, by the way, everybody, for.
Oh, thank you, Ben. These examples were very, very well challenging and curious. Like I think we're having fun. Kumar?
Yeah, thanks, Ben. I'm sorry, I've been preoccupied. We're getting ready to trundle across town here, so I'm a little out anyway. Thanks so much. This was really good.
No problem, buddy. You said you needed a step in, so I've stepped in. Undone all those years of physics you've taught them and just broken it all. Sorry about that. Now, Wissam had some points earlier.
John,
so
I'd like to recommend your next fish song to be the Mama Dance, because it's got a nautical theme to it, and since you're going to be on a boat for a few days,
Oh, what's
you
it
should have
called?
that song in your head.
Which
the
one?
Mama Dance.
Okay.
The Mama Dance.
All right.
It's a funky one, and it's nautical.
Is it more fish?
More fish. So I have a variation, not really a variation, but something similar to the boat in the canal bridge. So this was a funny problem that kind of went around in some sailing forums for a while, and the idea is like, consider the Panama Canal and the lock system. You have to pay more. You wouldn't be surprised to have learned that the big ships pay more than like little boats. If you have a little sailboat that goes through, they charge you something, but they don't charge you as much. And the thought occurred to somebody that that's actually not fair, because you gotta use a lot more water to raise the lockup for a little boat than a big boat. And then that just started this whole conversation about, wait, what? How do locks work? And is that even true? So if the price was like per gallon of water required to operate the system, the smaller the boat, the higher the fee should be. I think.
Well, you can. So again, you can say that's a really interesting. So I think what you're saying, Andy, is you've got a lock. So a boat goes into I think we know what a lock is, but a boat goes into this thing with two gates. They close the gate behind the boat. The boat starts at the level of the lower river whatever it is, you pump water in to this where the boat is, it goes up until it gets to the level with the upper river, and then the boat sails off. And you're saying, Andy, that you think it takes more something, let's say energy, to be specific, to raise a bigger boat. Now, I think you can just, I think it's, that's an interesting question, firstly. Does it? Clearly, the boat has much more mass, but you've also got to put in a certain amount of water. So that is an interesting question. I think the answer is pretty obvious, actually. But does anyone want to argue whether it takes more or less or the same amount of energy, regardless of the size of boat, to lift that lock up? That's a good bonus question. Hey, Kumar, by the way, you're welcome to speak up if you want. These sort of things, by the way, so here's another little technique I find pretty handy. It's called, I call it, well, the Latin is reducto ad absurdum. By the way, just quickly, Wissam, I have read your stuff. I agree with you. We shouldn't be talking about this from a single atom perspective. About the fly, it's more complicated. But really, I'm keeping the argument at the macroscopic level. Imagine a slow motion video of a steel ball hitting a windscreen, which has got plastic in it and therefore deforms a little bit. More elastically, confusingly, then I think the argument's fairly clear that ball temporarily stops, and therefore so does that part of the windscreen. When you get down to a lower granularity, atomic scales, I think it gets more complicated and subtle. So this lock, this ship, one way you could do this is reducto ad absurdum, which would be, you can look at the two extremes, right? Imagine the ship is like a grain of sand-sized ship, although that would sink, but a floating grain of sand, let's just say a tiny polystyrene ball. How much energy does it use to lift the dam? And then imagine the ship, the lock, and then imagine the ship now just about completely fills the lock and there's almost no water left. Yeah, good question. How much energy does it use in both cases, and is it the same? That is a good bonus question. I'm not just going to answer it for you.
To develop that question a little bit, there's a first reality, which is you can put more ships in a block at once.
Benjamin, your audio is too poor. You'll have to try again. It's really, really bad. So he's too bad. Does somebody else want to have a shot at this? Does it matter how heavy a ship? When you're trying, so this isn't one of the questions on the slides. This is a new question that Hero's effectively alluded to. You've got a ship going into a lock. You pump the water up, so lift the ship to the higher river. Let's say, does it matter how heavy the ship is?
How large
how
is
much
how
energy
long
do you need
and
to?
wide is the canal?
Maybe. I'm just talking about
what
the bit
is
where you
the
pump water.
surface area of the canal?
Okay, why do you think that matters?
Because of displacement. So, like, I'm looking at this water. You're kind of referencing the water bridge one, right?
Yes, but yeah.
I find it fascinating. What's the extra load on the bridge? Well, that again depends on how long and wide the entire surface area that you're displacing the ship's weight into, because you increase the water level of that entire like river-like structure by some amount.
Okay. Anybody else want to jump in?
Fundamentally, that is true, right? The more boats you put into a flat canal space, the higher the water level is. It doesn't matter whether it goes over this bridge or doesn't. It burdens the bridge as soon as you put it into the canal, but it's a diffuse
True.
burden. So, and there are limits, right? The canal has limits. It will overrun. The water will overpour at some point. So there is you can do a max weight on the bridge, and nothing can bring the bridge above it that max weight. So you have a static. So that's a solved problem. But Andy has brought in an unsolved problem, which is, does it take more water to lift a small boat in a lock?
Unsolved. It's not well, okay. It's not unsolved by humanity, but it's just unsolved currently by the room. While we just let them
Probably by
on.
humanity.
No,
if I haven't solved it,
humanity.
it's probably an unknown.
It's
an unknown state. So does the small boat take more water than a big boat to lift into the lock? And the first order estimate is that that's right because there's just less water in the lock. If there's more
Well,
boat in the
the
lock, there's
question,
less water in the
to be
lock.
clear what the question is, the question is how much electrical energy. Let's assume that the pump, let's not even go that far. Let's just ask how much energy it requires in both cases, right? Let's assume it's an electrical pump and it uses the same efficiency in both cases, running at the same speed or whatever. It's very clear that a boat that almost fills the lock is going to require almost no water to be added in comparison to the boat that is tiny, which is going to require nearly all of the water to be added. The question is, is there any difference in the amount of energy required in those two cases?
Well, that's not the question he asked. And the question he asked is actually more relevant
Well, I think it is.
because
Well, hold on. Let's let Andy say what the question he asked was. But I think that was the question because he was talking about the cost, the
wasn't the
best
question.
proxy.
Wasn't the
Well, the
question.
best. Well, Andy, you asked the question. What was the question? What do we want the
Well,
question to be?
well, that is a good question because I'm not sure I formed the question very well. It was more an invitation to finish forming the question, I think. So it's the thing is like how do you what's the is it about the amount of water? Is it about the amount of energy used? In the Panama Canal system, there's no energy actually because the water just flows from above, um, from the lake. The lake at the top is basically like driving the whole system. It's a completely
It's a
gravity-based
source.
system. Um, so an argument, I was, it's funny because when I stated it, I think I was believing the idea that it would take more water, but really I was posing the question: does it take more water, or less water, or the same? And an argument for it's the same be okay. A boat pulls into a lock, the door's shut. You're just putting water underneath the water. So regardless of how big the boat is, the additional volume is what you put in, you pipe it in below the boat, or you don't have to put it below the boat, but it's the change in volume, and that change in volume to get to a certain height is going to be the same regardless of how much
Well,
water is in the lock to begin with.
well, how about if the
um,
small boat only draws 1 foot and the big boat draws 20 feet? If
well, the
you've got to
difference
raise,
there, so if we're going uphill, the difference is you pull a vessel into the lock. A big boat is going to squish out a bunch of water before you close the door. A small
Displace
boat is
more.
going to squish out very little water. So it's
So
a
you have to use
matter of,
more energy for the smaller boat.
well, no, but that's just, I mean, the boat might be taking more. So we're talking about just getting the vessel into the lock. When that happens, a bunch of water is going to be displaced and it's going to flow. It's going to be down. It's going to stay at the low level. Then the door is closed, and then water starts getting either pumped in or drained in, whatever, however. So this is an elevator at this point, and you just imagine the difference in heights, and if you just put that water in at the bottom, imagine a big old, rectangle of water that gets added. That would be the same. The amount of
okay,
water
it's time.
added would be. I mean, that's the argument for why it would be the
It's
same, anyways.
it's time to go
Gotcha.
for
Yeah,
a
that makes
vote.
sense.
It's time to go for a vote. So who in text or in voice wants to say it's the same amount of energy whether we're lifting a tiny little dinghy or a massive super tanker in the Panama Canal as
Okay,
well?
here's the answer. It's the same amount of water and it's more energy to lift a bigger boat.
Okay, that's wrong. And somebody else want to give another answer?
Same amount of water, same energy.
Okay,
Is
that is
it
also
is it
wrong. So both of those are clearly wrong. Anything that says it's the same amount of water is clearly wrong because imagine you put a boat in. Well, it's just obvious, right? Because of the
But
amount
there's a
of boat, as
difference
Andy said,
between both
below the
boats
water.
enter, Ben, and they have the gate open, right? So the
So
moment that you close the gate,
yeah, the bigger the boat, the less water you have to put in.
Ben, do
Clearly.
you remember
yeah,
that
but the
feeling the
bigger
other
the boat,
day
the
when
less water that's
when
in. That's not the less that you have to put in order to get it to rise.
Okay, you sure?
somebody gave away the farm on this one, Ben, which is you need to think about filling up all of the water underneath the boats. That's the only water that's changing. The shape of the water at the
Yeah, but
top is
the
exactly the
amount of water
same
below
as
the
the
boat
bottom.
depends on the draw of the boat. That's what complicates that way of looking at it.
Nope, you just take the draw of the
If
boat,
the bigger
draw a
boat
straight
was
line.
dragging on the bottom of the ground,
No,
then
no dragging on the
yeah.
bottom. So anybody who wants to vote on it? We've got a couple of people. So we've got
Same
what do we
water, more
forget the amount of
energy
water.
for the bigger
Forget the
boat.
amount of water. Forget the amount of, just the amount of energy. So you're saying more energy, Benjamin. Anybody saying same energy? Who's saying same energy?
I'm gonna go. With it's the same. It's the
Yep,
same amount of
nice.
water
And
pumped in, therefore the same amount of energy for
for
going
a
up.
bigger boat,
It might be
or in,
different going down.
maybe different question. Let's answer the same. Let's keep the question stable. We've got enough variation in our answers. Anybody want to say that it's going to use less energy to lift a bigger boat?
I could be persuaded that it takes the same amount of energy to lift any number of boats, big or small.
Yep. I hope you could, because I think I'm very confident that's the right answer. So when we put a boat in, all we still have to give the system the same amount of gravitational potential energy, whether that system consists of pure water, i.e. there's no boat in there, or a huge boat where most of the gravitational potential energy is in the water and in the boat and less is in the water. It makes no difference. The level of the water is still going from the same level at the bottom to the same level at the top, and the boat only displaces its own mass. So it's just a reallocation of where the gravitational potential energy ends up. So I'm going to strongly assert that it makes no difference from an energy point of view on first analysis whether you're lifting a tiny boat or a huge boat. You still have to lift the same.
Or, and this is important, 7 tiny boats, which you can often get in the same lock space as
or 7
one
tiny
large boat.
boats. Yeah, exactly. Yeah, and that exactly.
But
So
in
the
that
only
case, it takes 1/7 of the energy to lift a small boat.
yes, indeed, exactly. So what you want to do is to have
And then it
boats.
takes more energy to lift a big boat.
It uses the same amount of energy to operate the lock regardless of what's in it if nothing's scraping on the sides or touching the bottom. So
Correct.
it's a fixed cost to operate the lock. But from first analysis, all your points, Benjamin, earlier about the speed, all this stuff, the amount of water, all those things are probably going to make a difference. How fast you can run the pumps, what flow rates the pumps are optimized for, the bore of the pump, loads of things, right? That's second analysis. But on first analysis, it's going to take the same amount of energy in both cases. And that's why, yeah, a big ship probably should be charged more. And if you're a little boat and they can put lots of little boats in together, then they can afford to charge proportionately less, as you say, a seventh maybe for 7 little boats, a seventh each. But just operating the lock costs roughly a fixed, which is a very interesting question, Hiro. But I'm confident in that answer, and that's
This is, I think, why they schedule locks. And you can see boats lined up in front of the lock for their schedule.
oh yeah,
Uh,
cool. So they can kind of do this optimization.
yeah,
Yeah, you kind of want to have a little lock
yeah.
party ahead of the lock and say, "Hey, dudes, you want to join me because it's to reduce the." I mean, you could literally leave it to Hansen or like this. Hansen, you're going to like these words. Are you ready? Hansen's going to salivate. Free market
Yeah.
economics. I said that just for you, Hansen, if you're here. Let me say it again, just because he's going to get
And
excited.
if he wasn't here, he would materialize instantly.
Free market economics. How's that, Hansen? How you feeling?
Bravo! All my neurons firing up. This is for wisdom. So Ben, you're soothing my neuron, and I'm soothing wisdom as well. So firing one after the other.
It's almost as if all the little boats could get together and say, "Hey guys, the ticket for lifting this lock is $700. How about we split it and give $100 each?" So yeah, free market economics
Right,
to the rescue.
trade.
Trade. And then, of course, I mean, always with these things. So I said in this whole room, and we are really coming to a close, we're doing a breadth first search of all of these 5 problems. What I mean by that is we're doing a first analysis first. What do I mean by first analysis? I mean, I gave you the analogy of searching a tree, trying to find the leaves. You can do that either by finding all the big trunks and then the second level trunks, then the third level trunks. One day you get to the leaves. I actually prefer that way in general because if you go the other way, which is go down to a leaf and then recurse back up one tiny little bit and down to the next leaf, you can be getting all excited about leaves of a tree, but maybe, as I say, one of the major trunks has all pink leaves on it, and that's much more interesting to look at. I kind of like breadth first, but it's, both ways work. It's a bit like the difference between top-down and bottom-up design. It's all good. I kind of like both, to be honest. The thing here that's interesting is that the skill, I think, sometimes with the physics is to understand what we mean by first analysis. It normally does just mean the simplest way of looking at it. But it can also mean, and that's all you can do in the beginning, right? It's just use what you've got. So you do the simplest. It can also mean having the wisdom to take the first analysis you do to be the one that is has the biggest and most dominant effects in it, if you see what I mean. That's not always using the simplest physics, by the way. So in a couple of these problems, we've used conservation of energy, which some people might find harder to grasp than force diagrams. Sometimes you'll use conservation of angular momentum. Sometimes you'll use E equals mc squared, for example. You'll say that heating this thing up must make it heavier by E equals mc squared, for example, and so forth. So sometimes first analysis means let's have a damn good guess at what the most dominant factor is here and talk about that first. And then you get some predictions and you go and see if those predictions work out and you do some experiments. And then if it's good enough, it's good enough and it's getting the job done. You're engineering things, you're getting results that can port to what you predicted. When you get things that deviate from that, that's when you go to like a second analysis and you start saying, it's a little more subtle than that, like with this canal thing. I'm sure that pumping a lot more water will be different in efficiency for all sorts of reasons. The ratio of the bore of the pipe to its circumference, which talks about how much water you can shift for a given unit of friction, and the optimal speeds of pumps, and the fact that the faster the pumps run, the more current they draw, and therefore the more voltage is dropped in the cables. There's a lot of other things we could consider and might be prudent to consider. So how do we know when to, just to finish this off, how do we know when to stop? First analysis, second analysis, third analysis. And then the simple answer is when it's good enough. When it's good enough and getting the predictions you want and the results you want and you're engineering the shit you want, it's good enough. Sometimes you need to go a step better for competitive reasons. You need to do better than your competitors. Sometimes you need to just run really thin margins in business and you need to optimize the hell out of your canal. So you realize that this whole, it's a fixed cost to lift it up regardless, is not quite right. And if we can charge differently to our competitors because we have a more accurate pricing model, that could give you an advantage, and so on and so forth. But good enough is good enough, I think, is the bottom line. And there is no end to it. There is never an end. You can keep going and going and optimizing. Well, there's nearly no end to it. So anyway, that's a little spiel there. I've enjoyed the room. It's been better than I thought. I didn't prepare it as well as I'd like to have done, but it actually worked out just about right for time. I'm nearly out of time and probably should end the room when I am, but if Shamash, Hiro, or anyone else wants to run a follow-up room, that would be fantastic.
Just want to add thing quickly.
Let's let Hansen go.
Yeah, just want to add quickly. I think your answer for the waterlock is correct, and but here's probably a even simpler one. Maybe it's already covered, but so basically, what matters is just the water level before and after the if you want to.
That's what we said. Yeah.
Yeah. So and you just the energy is just the how much the same going lifting before and after how much water you lift with that bottom area times the height difference. That's all there is. So long as you it doesn't matter what shape, whatever the size or whatever boat it is.
Yeah, no, I agree with that. But it's a bit like the thing that John did with the floating a couple of weeks ago. That type of answer that both you and I have given a very similar answer, Hansen, is I'm sure correct and is a first analysis correct answer. It's one step to just write that out, a little bit more of a step to write out just to prove that it doesn't really matter how high the boat floats in the water or any of that, just to show that the boat's mass cancels. That would take a side of A4 and another 10 minutes just to let people know that kind of qualitative argument that Hansen and I have given is a bit hand-wavy. I think you can trust in the case of Hansen and I that both of us could go away and do the maths and give you a one-sider that proves it within 10 minutes. But as an exercise to the reader, to you guys, go and do it if you want. If you're able, try and just do the maths and show that. Because that's what's really satisfying.
Wait, did everybody get to the point that it's the same amount of water, regardless of the boats?
No, I don't agree it's the same amount of water. I don't think I agree. What, Hansen, do you think it's the same amount of water regardless of the size of the boat? Or just the same
Here's
amount of
the
energy?
visualization, if you will.
Hold on, let's
The
just get
state
Hansen's
of
answer. Yeah, just because I haven't got limited time. Hansen, would you agree it's the same amount of
water? It's the same. I mean, energy is just if you think. I mean, actually, I mean, it's very straightforward thinking. Basically, you should use Archimedes principle, everywhere when the thing's floating. So just replace the whatever boat with the same volume of water. So just replace
It's just
anything
You
exactly
don't
just
with the
replace the
Archimedes
water.
boat
principle.
with
So
the volume of water.
Yes,
hold on, guys.
exactly.
You
So
replace the boat with the mass of water.
It's not.
okay,
It's
so yeah,
it,
so just all it is just this water level water, and then we raise up to the next level. That's all you need to think about. That's it.
Yeah,
yeah.
but
So
I think that
Benjamin,
wasn't
the thing.
responsive to the question. The question
So
is
yeah,
the same
Benjamin,
amount of
I get where you're
gallons.
going with it, but I'm really out of time.
Yeah,
So
the volume is not the same.
let me tell you what you could think
The
about.
volume
The
is the
volume.
same.
No, the volume is not the same. But let me tell you what you could think about
Is
to convince. It's definitely not the same. Let me tell you what you could think about to convince yourself. You want to think about integrating the pressure, the water pressure, over time as you pump up, and think about how that's different in the case where there's a boat of negligible size
It's
to a
even
boat that
easier.
pretty much
It's
that
even
fills the lock.
easier to
I
just
know on first
yeah.
analysis, Hanson, it's just Archimedes principle.
Oh
But if
no,
Benjamin wants
just
to know the
yeah. But
mechanics of that,
I just want to. This is a very good method. Just take it to the extreme. Take it to the extreme. Think about if you have a box, right, and then you have a boat that is exactly the almost the same shape as the box, and then there's a sliver of water in it, and then just the holding the boat up, and then you try to pump the water up, right? How much water do you need? Infinitesimal.
exactly the same amount of water.
Not in the same amount of water. You just
I agree with Benjamin on this.
lift the same height.
Yeah.
All right, so lift
The
the
boat is
same height.
floating the whole time. The boat is floated. The boat is never not floating. So you don't. The question isn't if I'm filling up a dry dock, how much water do I need? The question is how much water do I need to shove underneath the boat somehow? Just keep it under the boat. So that block, that volume, that block of water is the same. Even if you were just lifting the other water up. If there was no boat and you just had to lift all that water up
yeah.
higher,
But Andy,
it's the same.
the problem with that argument, right, is that when the boat pulls in, there's a certain amount of draft available, right? It doesn't matter how much draft. There's a certain amount of depth available. So a big boat would fully occupy that initial available depth, and a small boat would use almost none of it. So if you're talking about how
Actually,
much,
yeah.
But the small
so
boat
just think about
water's
that.
already there, so you don't need to
Actually,
pump it in.
okay. So in this case, Benjamin is right. So the what is this is basically it's the
Wait,
same
Hanson, you're
principle.
breaking up. You just gotta
Oh,
start again.
okay. Can you hear me?
Yeah.
Don't fall for it,
Yeah.
Hanson.
The so Benjamin is right because the same principle as illuminating earlier. So you have so replace the boat with water, right? And then you basically raise the level to from before to after, and then the amount of water you pump in, and then the energy needed is how much energy you need to pump the water
Yeah,
or just lift the
I
whole
agree.
thing up
I
to
agree now as well.
the
So
weight.
Benjamin, your initial assertion was that the water is the same and the energy is different. So you were right on the water is the same. I've now considered it more carefully, and you were wrong on the energy is different. To be clear, so Benjamin was half right, which is a good win for him.
Oh, well, actually, I'm just saying that if the water, if the
So sorry. He initially said the water was the same and the energy was different, and we know that the answer is the water
okay,
and the
so
energy
No,
are the
no,
same.
no. The energy to lift big boats is more in a lot than the energy to lift small boats.
No, we've already agreed it's the same, buddy.
so whatever it is, it's just the difference in the height of the water, and then the amount of water, the energy. Of course, I mean it's the weight, the area, bottom area times the height. That's the amount of water you need to pump in, and then the energy of lifting that amount of water from the original height
Right. But the reason
to
I'm
the
going to be
final
right on
height.
both
That's it.
counts and not just one here is that you can put more boats if they're small in the lock
That doesn't
and
Well,
that
fewer
doesn't
boats if they're big.
that
it
doesn't matter,
doesn't
buddy.
matter, right? I mean, you can
That doesn't
do
matter.
whatever
That's
you
right.
want.
It doesn't matter. But
It
the
doesn't matter
point
how many.
is, if you have a small boat, you can lift 100 of them, and if you have a big boat, you can
No, but
only lift
so
one.
you're
And
just trying to
therefore,
shift the argument. You're
the
trying to
big
shift the
boat,
argument. Hang on, you're trying to shift the argument to energy per boat now to try and make yourself right. That was never the question. It was never
correct,
energy.
correct.
Yeah, but that's
But you
assuming
will
that.
agree with me that energy per boat
Yes, I'll agree
is
with you with
relative to
energy
the
per
size of
boat.
the
But
boat.
what you're trying to do is shift the argument to that as if that's what you meant in the first place. That was never the question. The question was always what's the total energy the lock has to expend, because we were talking about how much you should charge a big versus a little.
Well, that's not right. No, because the
Anyway,
amount you should charge is relative to the energy
sure.
consumed. And it turns out the energy used for a small boat is less.
Not if
And the
it's on its
water
own.
used for a small
Not
boat
if it's
is less.
no.
Correct. Not that's right. Not if it's on its own. That is correct. But it is
Yeah.
never on its own.
So Andy, I got it wrong, and Hansen at first about the volume, because I didn't even try and think about that in depth. We didn't, just like hand waving that one. Andy gave a very convincing argument. However big or small the boat is that comes in, it's the same thing. If it's a small boat, the extra water's already there. If it's a big boat, okay, there's hardly any water around the sides of it. Doesn't matter. You still have to pump the same amount in below the bottom of the boat. I like that argument. That's very clear. Yeah, and then the other question was about energy, and clearly it's a fixed amount of energy. And if there's if you probably should charge smaller boats less from a free market point of view anyway, because the energy per boat is a lot less.
Because they
So
use less energy and they use less water.
then, what do you mean that per boat? Yes, so less energy and less
Yes,
water
per
per boat.
boat.
Yeah, per boat. Yeah,
Right,
sure,
right.
and that's fine.
And even if you show up alone and they have to operate the whole lock just for you, the pricing schedule is sort of amortized over the experience of the whole year. And overall, smaller boats take up less room. In fact, they probably get a free ride with the bigger boats and just jam them into the corners when they go
Yeah.
up.
That makes sense, and the economics would say that you should just split the fixed cost basically. First analysis, fixed cost per lift. If you're on your own, it's going to be expensive. If you're alongside a big boat, go for free. Yeah, all good. So good one. Thank you, Andy, for your bit on there. I liked your argument about the water. I was definitely wrong on that, and Hansen came out the gate wrong as
If
well on
you
that.
like
And
these shows where Ben is right in the end, quantum mechanics has an update, and that is that D-Wave is now in a court hearing. Speaking of free market, it's being accused of fraud. That will be
fun.
fun to watch.
Yeah,
Is
let's see
that
how that.
true or is that really? I mean,
Guys, I've
Yeah,
got
yeah, yeah.
to
There's
I've got to disappear though, because my food's literally on the table. So if anyone wants to start a side room, I'll give you a minute or two to do that, so that you can kind of bridge people over to it. Is anyone going to start a side room? Hero, Shamash, Benjamin, anybody?
Andy, will you start the
If
room
somebody
here?
starts it, I will definitely go over there. I can't start it because I'm driving.
All right, I'll start a room in Ben's house.
You can, yeah, that's fine. Over in the Smart View house or whatever, or just on your own house, whatever, Benjamin. And I'll see you guys soon.